Hello everyone, thanks for watching this video. I am Marco Antonio Rios and I will present my work running efficiently CNNs on the edge thanks to hybrid SRAM and RRAM in-memory computing. Edge artificial intelligence, or edge AI, is a deployment of artificial intelligence algorithms on edge devices. As example, wearable health monitoring systems that use artificial intelligence, facial recognition on smartphones or security cameras. They use convolutional neural networks, a very data-intensive kind of application, augmented reality, and so on. In recent years, it became clear the need to bring AI inside edge devices, as it enables a more private and secure data analysis, important for sensitive data because the data is no longer shared on cloud service. More responsiveness. It enables real-time data analysis that is very important for health monitoring, for example. However, some applications are not possible to be deployed on edge devices as convolutional neural networks due to the low power budget and computational capability of such devices. Applications considered data-intensive expose a problem on conventional architectures. A lot of energy, actually up to 90%, can be spent only on data transfers between the CPU and the memory. So edge devices need a new solution to enable edge AI, and this solution is in-memory computing. Blade is an example of in-memory computing architecture, and it stands for BitLine Accelerator for devices on the edge. It is based on BitLine computing on a static RAM memory, or SRAM. We access 2 or more word lines at the same cycle clock instead of 1. As a consequence, we observe the bitwise operations NOR and AND between the accessed words on the bit lines. Blade is the only BitLine logic architecture that can perform high-frequency operations and use high-density bit cells at the same time, and that is consequence of the local group organization. At the bottom of the Blade subarray, it is attached a logic block for each set of bit lines, which enables a variety of operations, all kinds of bitwise plus shift and additions, and they are executed in 2 cycles, one for the in-memory computing and other to write the data back to the memory. The operations read and write are conventionally done in 1 cycle. Blade also performs multiplication and consequently convolutions by doing shifts and additions one after the other. So why we need a hybrid architecture? In this slide, I will show you the reason. Edge AI requires custom solution that depends on the application. In this case, we are optimizing the in-memory computing architecture to run efficiently convolutional neural networks that is used in video analysis, image classification, language processing, new drugs discovery, and so on. CNN has basically 2 types of data: activations, so the inputs of each layer, and the CNN model that has millions of weights. In each inference, the activations are different. On the other hand, the weights rarely change, only when the CNN is retrained. These data have different runtime patterns. Such behavior can be exploited by using hybrid memory technology, combining the SRAM for the activations because of its high endurance for write operation, as opposed from the resistive memory, and the low write energy. The resistive memory can be used to store the weights, so the CNN model, because of its low leakage, the non-volatile behavior, and the high density of integration. Here I show the hybrid SRAM-RRAM in-memory computing architecture. I designed a resistive local group that is compatible with the SRAM and enables in-memory computing operations to happen between the distinct technologies. The local group was physically designed considering the 28 nanometer CMOS technology from TSMC. In order to enable the in-memory computing operations, it is mandatory that the technologies or the local groups are aligned as they share the same set of bit lines. Therefore, the resistive bit cell was designed respecting the 500 nanometers pitch from a high-density SRAM bit cell. It was placed 2 cells side by side to comply with this constraint. In consequence, the resistive local group has 2 bit lines. Each one is connected to a column of resistive bit cells. During the read operation, one bit line is connected to the bit cell that you want to read, and the other is connected to the reference circuit. They are pre-charged, and then the sense amplifier compares the voltage drop of the 2 bit lines, finally latching itself. Then, as shown in this figure, enabling all the range of in-memory computing operations. As mentioned before, the resistive local group on this hybrid architecture is intended to store the models. However, the models of the CNNs have orders of magnitude more weights than it's possible to store on the resistive local group. If we blindly use the resistive local group to store the models, we would need to constantly update the weights, fast depleting the write cycles available for the resistive memory. Therefore, we need to go one step further, and here I present the weight data mapping. Imagine that this matrix is the CNN model, and we quantize it in 5 bits. Instead of storing all the metrics, weight data mapping proposed to store only the unique values on the resistive local group. Here I bring one example of subarray organization. The unique values we can store on the resistive local group, while the activations we store on the SRAM. Like that, we are still able to perform the operations between the distinct local groups. We just need to change the manner we access this data. In order to measure the improvement that this architecture can bring, I developed a cycle-accurate simulator. It receives the CNN structure. It is only based on the geometry, as the values of the weights does not change the amount of operations the inference will need. It also receives as input the macro memory information, the subarray specifications, number of resistive local groups, SRAM local groups, and so on, and also the amount of subarrays. Then, the simulation performs a layer-wise analysis, defining the necessary cycles to deploy it in terms of data transfers and in-memory computing operations. The considered CNNs are AlexNet and MobileNet. Moreover, the number of subarrays range from 1 to 128. Here I present the output of the software for the mentioned CNNs and the subarrays. And I compare the hybrid architecture with the conventional blade, only SRAM without weight data mapping. Here I call it homogeneous architecture. In green is the number of in-memory computing operations required. This curve is equal for both the hybrid and the homogeneous, as the number of in-memory computing operations depends only of how much we can parallelize the operation. On the other hand, the data transfers drops up to 60 times. To assess the energy consumption, I considered a scalable H3 and did the characterization of the energy necessary to transfer the data from the border to the subarray. I also characterized the subarray to assess values of leakage. The hybrid architecture has 20% less leakage compared with the homogeneous, while presenting 7% more bit density. Now, considering a full inference of AlexNet and MobileNet with 128 subarrays, the hybrid architecture showed 93% gain in terms of energy on both applications, while showing a performance gain up to 6.89 times. That means that we now can perform inferences of MobileNet on the edge at real time, 22 frames per second. So on this presentation, I have shown how to efficiently run CNN's inferences on the edge, thanks to weight data mapping and hybrid architecture. Weight data mapping can reduce up to 60 times the data transfers. And with that, I have shown 93% energy efficiency improvement and up to 6-time performance gain while performing a full AlexNet and MobileNet inference. That concludes the presentation. Thanks for watching.